Hello, my name's Hutchinson. I'm a fourth year MN Civil Engineering student from Teesside University. My pitch today is all about structural engineering in nature, which is my third year project. So, to encapsulate my whole pitch, I just want to start with the Eiffel Tower. The Eiffel Tower exhibits a structural engineering design that we see in nature every single day. It's basically a big tree. Trees are a natural cantilever. You've got wind loads acting down the side, the branches are very thin at the top, get wider and wider and wider, just like the tower, where the bending moment is a maximum. It's a perfect example of structural engineering in nature. So, I want to look at the skeleton. To briefly introduce you, the skeleton's effective, it's successful as a structure, it's efficient because it produces maximum productivity with minimum wasted effort, and it's durable because it lasts us a lifetime, despite the marathons we're not meant to run. So, we've got four main components: bones, ligaments, tendons and joints. It's all about the synergy of these four coming together, and how if you stand on one leg, you can balance. It's basically, they produce a combined greater effect. So because the skeleton is such a complex structure, I've decided to focus just on the hip, where your femur, your longest and strongest bone, joins into your pelvis at a ball joint. It's absolutely crucial in supporting the body in dynamic and static postures. So a bit of basic research. It basically works like a roof truss at home. You've got struts, which are your bones, your compressive members being pushed together. You've got ties, your tensile members being pulled apart, your ligaments and your tendons. You've got localized strengthening, places that need to be stronger, like your hip joint are, places that can be weaker, fingers and toes also are. And all these changes in properties, size, shape, density, change depending on the location in the skeleton, hence why bones aren't regular. So, when you look further into it, it's not just bones in compression and tendons and ligaments in tension. You've got tension and compression within bones. So, bone is a composite material. It's hard and fibrous on the outside, your cortical bone. Inside is soft and spongy, the cancellous bone, which is really light, gives a high strength to weight ratio. When you apply load to the top of your femur, you get this mesh that forms a huge tensile arch that overlaps with two zones of tension at a perpendicular. This mesh is incredibly strong, and it's very efficient at transferring load down the femur. So you can see that there on that scan. Tensile arch, two zones, nice and dense, but you do get this zone of weakness. So it wouldn't be a good project without a bit of experimental data. Because it's unfortunately unethical to test on human femurs, I went and got 4 cow femurs. Thanks, Mum, for the freezer. And I just really wanted to get an understanding of how load does transfer down them. If you're a bit squeamish, you might not want to look at the next slide. That is before and after you apply a load to the top of a femur. It's absolutely amazing. These weigh 2 kilograms each, but held 3.7 tons. A whole Land Rover sat on top of it. So, why am I doing it? I want to understand where structures need more support. If we can mirror these joints that we find in the hip, if we can mirror the hip joint in structures, we can provide efficient, safe, durable structures. And how can civil and structural engineers be more influenced to get more from their designs and their materials? Thank you.